Good afternoon, everyone. As per revised timetable, so we have one more live session. That is today's live session. It is actually one additional live session which we got as per the revised timetable. Right. In today's session, what we'll do is, I hope my screen is visible. All of you can see my screen, the PPT which I am presenting.
Yes, sir.
Okay, yeah. So in today's session, we'll try and see a practical coherent detector, that is a Costas receiver. Right. Someone was trying to join. Yeah. Okay. Fine. Yeah. A Costas receiver and one way of actually multiplexing two different signals. I hope you know what is multiplexing. Multiplexing is nothing but what transmitting different signals over same channel, right? So how can we use the concept of this coherent detection, or can we exploit the fact of quadrature null effect to multiplex two different signals, right? Within a channel of bandwidth, say W. That's what is quadrature multiplexing. Before that, so in last session, which was a recorded session, I had posted a video on coherent detection. So maybe coherent detection, as we have seen, it's actually what an ideal mathematical model of a perfect DSBAC detector, right? And in today's session, we'll be seeing a practical approach, that is a Costas receiver, right? So, and before that, I have received many questions or doubts regarding the ring modulator, right? How sorry, a ring modulator suppresses the carrier, right? So why transformer is used, right? All those things. So I think before we move ahead and discuss with this Costas receiver, I'll take some 5 minutes to discuss on maybe give some more clarity on that ring modulator, right? So then after that we'll proceed with today's topic, right? So if you remember, the ring modulator, it essentially had two transformers. So one side in which we are feeding the message, that is actually an audio frequency transformer, right? And it had a ring of diode, right? It had a ring of diodes, right? So it will be, yeah, it had a ring of diode, and we had one more transformer, right? And one more transformer, and output is taken across the other transformer, right? So this is and all both these transformers were actually what sender tab transformer, right? Sender tab, and we were telling both should be completely balanced, right? So we'll be feeding C of t, which is a square wave here, C of t, which is a square wave here, right? It need not be square wave, it can be any wave, right? Any wave, if provided these two transistors are perfectly balanced, right? And all these four diodes are identical, right? So this can be any way, but for our convenience, we can consider it as a square wave with amplitude 1, right? So it will swing between +1 and -1, right? So now we are giving messages. So initially, maybe for you to appreciate the working of this, we'll consider we have not given message signal, right? If message signal is not given during positive half cycle of the C of t, what will happen is diode D1 and diode D2 will be on, right? During positive half cycle, diode D1 and diode D2 will be on, right? So what will happen is, and one more thing, I can show the polarity here. This is plus and this is minus during positive half cycle. So during positive half cycle, D1 and D2 are on. So this is plus and this is minus. So you can see whatever be it, right? It's the upper half and lower half, they are symmetric, and current will flow in this direction. If you can see, right, current will flow from, right, positive potential to negative potential. So in lower half, current will flow in this direction. In upper half, current will flow in this direction, right? And as long as these two parts, upper and lower part, or this center tap is exactly at the center of this, say, a secondary of this audio frequency transformer, and primary of this radio frequency transformer, right? So what will happen is the current flowing in upper part and lower. So current I will be flowing downwards, and the same current I will be flowing upwards. So what happens is the net current, or net current which will induce some voltage in this, will be equal to zero, right? Or else there are equal and opposite currents. So the voltage induced in the secondary will be zero, right? So voltage induced in the secondary will be zero when m of t is equal to zero, right? But if m of t is present, what will happen is, maybe we can consider superposition, right? So even though the contribution of C of t to the secondary of RF transformer is zero, right? Of course, the contribution of m of t will be there. M of t is not actually what fed across the center tap, right? M of t is the total. M of t is given to primary of this audio frequency transformer, and it is actually what induced to the secondary of audio frequency transformer as a whole. It's not fed across the center tap, right? So because of that, whatever, right, part of M of t reaches here, primary of this RF transformer, it will be actually what available at the secondary of RF transformer. So here we are using the C of t only to switch on and off the diode, right? We are using the C of t to switch on and off the diode. So when I say diode is on, it means actually what C of t is equal to 1. When I say diode is D1 and, sorry, when I say D1 and D2 are on, that is when C of t is equal to plus 1. When D3 and D4 are on, that is when C of t is equal to, say, minus 1. So just now I have explained only uh, what happens during the positive half cycles, but same thing during negative half cycle also, same thing will happen. But because these diode D2 and D3 are conducting, and polarity will be reversed, here it will be plus and here it will be minus, the direction of current flow will be reversed. So the polarity of the voltage induced at the secondary of RF transformer will be different. So that's why, that is how this a combination of AF and RF transformers can nullify or suppress the carrier, right? And only M of t is passed. So you can see the C of t as a switching wave, right? It will make any two of these four diodes on or off at a given time, right? So that it will allow whatever is there in input, right? In one case, input will be passed to output as such without any phase reversal, but in second case, there will be a phase reversal, or polarity of the um, output will be opposite. So that is how we can explain uh, the working of ring modulator, right? So now I hope it's clear. So is there any doubt regarding this? Right. So if you have any doubt, please feel free to ask. Or if anyone understood, I don't expect everyone like understanding it when first time when I say this. But if any one of you understood, please do let me know. Right. Did anyone understand what I explained? Anyone? I'm not asking what to someone represent the entire class. Right. I'm asking individual. So if you understood, please do type in chat window yes, right? Others need not type anything, right? So please. Okay, right. So please don't think if some of you understood, some others may not have understood, right? So when I ask, did you understand? Someone is typing yes, right? I won't consider it as actually what response from the entire class. I won't like consider it as actually what representation from the class. It's individual's opinion. I appreciate that. Right. So please feel free. If you didn't understand, you can tell no. If you understood, you can tell yes. And what about others? Right. What about others? I need some more inputs. Right. So yeah, please. It would be really great if others also can type in something in chat window. Right. So I can't see any no yet. Right. I'll maybe I'll wait for say 30 more seconds. Right. Then randomly I may ask someone to explain. Right. So I'll take here silence as yes. Right. I'll take silence as yes. Then if I ask someone randomly, you should be able to explain me the concept. Right. I think all of you have access to what typing in chat window, right? Okay, maybe I'll ask someone. Um, yeah, Ryan is there. Ryan, voice. Ryan, can you please unmute? Am I audible to everyone? Anyone give me feedback for that? Am I audible?
Yes, sir. Yes,
Yes,
sir.
yes. Okay, fine. Thank you. So, Ryan, can you please unmute? Yeah, Ryan. Yes, Ryan, are you trying to speak something? I can't hear you. Yeah, okay. Maybe if you have an opinion in between class, I should not ask any questions. I should not expect it to be interactive. If you have such an opinion, please do type it in yes. Hmm? So that like, it's easy for me actually. What I can just keep on discussing the topics and I can finish the syllabus. Right? Should I do that? Is that what you expect? Yeah. So that again, silence. So silence means yes, I guess. Right. So I'll take from now onwards silence as a yes. Right. So so basically I'll just revise what happens is in a ring modulator. Right. In any of the half cycles of the C of D, the current flowing in primary of the second transformer, that is the RF transformer, right, it will be equal and opposite. So in effect, right, uh, the current will be zero. Current which can uh, induce a voltage on the secondary of an RF transformer is zero. That's how it can suppress a carrier. Here, carrier C of D, it is used only for switching on and off the diode. So that's how it can suppress the carrier. Right. So okay. With that, we'll move on to the next topic. That is Costas receiver. Costas receiver is a practical coherent detector. Right. So a coherent detector, ideally, it will have a product modulator and a low pass filter. Right. So a product modulator and a low pass filter. Right. So Costas receiver is a practical coherent detector. So, if I ask you what was some of the practical difficulties in implementing a coherent detector, if you have only a product modulator or a multiplier and a low pass filter, right? It will give us some trouble at times. What was that issue? Right. So I've assigned a video yesterday, and at the end of that video, one open-ended question which I had given was list down in your own word the practical difficulties of implementing a uh, coherent detector. as such, right? So what was that? Anyone remember that? Anybody remember that? Tejashree? Yes, Tejashree, you have to unmute yourself and say hi to everyone now.
Yes, sir.
Yeah. So do you remember what was the practical difficulty? Or else I'll make the question more specific. What was a quadrature null effect?
Yeah, yesterday I didn't watch the video
Yes.
because I didn't had data. So yesterday I didn't
Yesterday
watch.
you couldn't watch the video, so you didn't have data. Okay, okay, fine. So anyone who watched the video, may I call Abhirama KV. Abhirama, can you please unmute? Right. So when I request you to unmute, please do. Abhirama has typed some. So okay, Pradiksha has typed there will be arbitrary phase difference. Yes, that is the correct answer. Right. So when I ask someone to unmute, right, despite the fact that whether you know the answer or not, you can unmute and say, "Sir, I don't know." Right, not a problem. Like still, only yesterday I posted that video. I know some of you have not watched it yet. Right. So right. So when I ask you to unmute, please do unmute. So Abhirama, can you please unmute? Aishwarya, is Aishwarya, please unmute and say a hi. And at least if you have some issue with your mic or problem with unmuting, you can show the courtesy of typing it in the chat window. Right. Hmm? And those who are not responding, right? Anyway. Okay, even Aishwarya didn't watch the video, right? So then, can I have Hima unmuted, please?
Yes, sir.
Yeah, Hima, did you watch yesterday's video?
Yes, sir.
Yes. So, what was the issue with coherent detector?
Uh,
It had something to do with actually what phase synchronism, right? So coherent detector had a local oscillator which will generate a carrier locally, right? So same carrier frequency locally, right? But of course, uh, if we can assume frequency is non a priori to the receiver end, but phase, right, synchronization, it's a big problem, right? So if there is an arbitrary phase difference, what will happen? If that phase difference is a constant over a period of time, it won't give any trouble, right? But if that phase difference is fluctuating, what will happen is the envelope which is detected or the demodulated signals, its amplitude also will fluctuate. And whenever this phi is equal to pi by 2, right? Whenever this phi is equal to pi by 2 or odd multiples of pi by 2, the phase difference is pi by 2 or odd multiples of pi by 2. What happens is this half AC cos phi, that cos phi will become 0, so we will not get any demodulated signal, right? So that was the issue. So you can please mute him up. Thank you. Right. So that is the that was the problem. So to overcome that, we told we should have a precise phase synchronization. So the carrier which is used at the transmitter side, C of t, AC cos 2 pi FCT, right, and the carrier which is generated locally at the receiver end should be phase synchronized, right? So for that we have some setup in this Costas receiver, right? So you can see Costas receiver, it is actually what a practical synchronous receiver system or a coherent detector system, right, for demodulating DSP-SC. So one more thing I would like you to keep in mind this coherent detector or this Costas receiver, it is meant for DSB-SC demodulation. Right, and one modulator for DSB-SC, what we have learned is ring modulator, which we have already discussed. Right, so it's a practical synchronous receiver. Right, so maybe first we'll see what are the components in this. Right, so we'll see the construction. So as you can see, it consists of two. Maybe I'll use a laser pointer so that you can. Right, so it consists of two coherent detectors supplied with DSB-SC wave. So what was a coherent detector? Coherent detector is nothing but what a product modulator followed by a low pass filter, and of course there will be a local oscillator. Right. To input will be giving DSB-SC modulated signal, and output of the low pass filter will be uh, message, of course, with some like amplitude scaling. Right. So here we have two sets of coherent detectors. You can see one on the top, we call it I channel, and other one in the bottom, that is Q channel. Right. So both are supplied with actually what individual local oscillator signal. Right. So there is something. So maybe I'll come to this part later. There is a voltage control oscillator, basic discriminator, and all. So this VCO is our oscillator, voltage control oscillator. It produces right the carriers for I channel coherent detector and also for the Q channel coherent detector. But you can see the carrier or the signal which is fed to I channel coherent detector is cos 2 pi FCT plus phi, and what is fed to Q channel is actually what that shifted in phase by a minus 90 degrees, so that it will be sin 2 pi FCT plus pi. Right. So that is another thing which you have to keep in mind. Individual local oscillator signals are in phase quadrature with respect to each other. What do you mean by phase quadrature? They are 90-degree out of phase. For example, cos and sine. Right. So that part is clear, I think. So we have two um, coherent detectors. Right. Two of them are fed with local oscillator signals. They are in phase quadrature with each other. Right. Now for the uh, one more thing which you have to keep in mind is the frequency of the local oscillators. It's FC. Right. Is should be same as that of the carrier frequency, which is used at the transmitter end. Right. So this frequency should be same as that of the carrier frequency, but that is obvious. One can easily actually what get to know about that. Why? Because if you are using some, if say AM radio, the carrier frequency, right, it will be a fixed value. Right. So you can design an oscillator which will produce that particular frequency. That is not a big deal. Right. So we can produce that. Right. So now FC, the carrier, the frequency is FC. Right. Then we can see this I channel and the Q channel. Right. I channel and Q channel outputs are coupled together. Right. And it forms some negative feedback system. It forms a feedback system. Of course, it's a negative feedback system. It forms a feedback system. Right. So in that feedback path, we do have a phase discriminator and a right voltage controlled oscillator. Right. So what it does is, this phase discriminator, it should be able to discriminate the phase difference between this I channel output and the say Q channel output, or else it should be able to identify what is this phi. Right. So maybe while explaining the working, I'll explain that in detail. Right. So this phase discriminator, it will give some output signal which will be proportional to this phi. Right. So we can call it as error signal or something. Right. So that error signal will in turn actually what uh, control this VCO. Right. According to this error signal, VCO will adjust its output so that the phase error will be reduced. Right. So that the phase error will be reduced. So that is what was the construction. So this I and Q channel, as I told, it is given to a phase discriminator. So a phase discriminator, basically it consists of a multiplier followed by a low pass filter. Right. So a phase discriminator consists of a multiplier followed by a low pass filter. So now if I ask, right, so maybe I'll Right. Suppose you have a multiplier and you are giving cos A and sin A. What is actually cos A sin A? Can anyone tell me that, please? Right. I need help. Right. Sin A cos A. Yeah, I'm asking about the trigonometric identity. What is sin A cos A? Like cos A cos B, we have right. We have already seen. Right. Or what is cos sin A cos B? Or right? Can anyone give me an input? Right. What is that? No response. Right. So okay. Now I'll ask you to what find out an answer for this and question to the working of the space discriminator. Right. If you expand this cos A sin A, right. So maybe if I ask you what is 2 sin theta cos theta, you may have answer. Right. So if you expand that, right, so you'll get two terms, right. So in that one term will be a low pass term, another term will be a high pass term. So a multiplier will, if you give, I told yesterday itself, if you give uh, say two signals to a multiplier, it produces sum and difference frequencies. Right. So it will produce actually what, a component which has frequency 2a and another component which has frequency a minus a, that will be 0. Right. So I'm asking you to what, to try it as a homework. Right. So if you give two signals to a product module, right, uh, it will produce sum and a difference frequency. So in this case, right, the frequencies are same, right? So if it is a and a, the sum will be a plus a, that will be 2a, and the difference will be a minus a, that will be 0, right? So instead of a and a, one is cos a and other one is, if it is cos a plus 5, right, one is cos a, another one is cos a plus 5, right. What will be sum will be 2a plus 5 and difference will be 5. So there will be a sin phi term left out, right. So that is the basis of the how this phase discriminator, right, which in turn is actually what, a multiplier followed by a low pass filter, how it can give us the phase difference between two signals. So it follows from the very basic trigonometric identity, right? And you should know what a low pass filter is. So those are the two requirements for you to appreciate that concept. So right. So then, if we have signal which is, if we have some signal which is proportional to phase here, so then that phase, it will actually what, correct the output of this voltage control oscillator. That is how it works, right. So phase discriminator outputs a DC controlled signal that automatically corrects for local phase errors in the voltage control oscillator. So that is the construction and almost working of a Costas receiver. So maybe what we can do is we can try and write down. Right. So let us. We'll just see what happens in this I channel initially. Right. So I channel input to this is AC cos 2 pi FCT in M of t. You are multiplying it with cos 2 pi FCT plus pi. Right. So what happens is, yeah, maybe AC cos 2 pi FCT into M of t times cos 2 pi FCT plus 5. Right. So we are multiplying. So what we get is AC cos 2 pi FCT into cos 2 pi FCT plus 5 times M of t. right? So if you multiply this cos A cos B, right, cos A cos B, right, it will be AC times, right, maybe m of t, I'll like take it here as it is, right, outside, then we'll get half cos of 4 pi fct plus 5, right, then plus what is 2 pi fct minus 2 pi fct, it will be 0, so it will be plus cos 5. So this cos 4 pi fct, I've been telling this even before itself, right? So this cos 4 pi fct is nothing but what, a signal with frequency, a cosine with frequency 2fc, right? And this cos phi, right, it will be a constant at any given time. It's not right at any given time, it will be constant. So what we have is AC m of t half cos 4 pi fct, so it's a high frequency term, right, and this is a low frequency term. So when you pass it through a low pass filter, only this term will be uh, allowed, this will be suppressed. So that is how the I channel works. So similarly, Q channel also, instead of this cos, you replace it with sine and try to find out what happens, right? So that's what is written here, half AC cos phi into m of t, right? So now I think you will be able to uh, appreciate it, right? So that is half AC cos phi into m of t. So similarly here we will get half AC sin phi into m of t, right? So now let us just see, right, what happens when phi equal to 0 initially. So for you to explain the working of this, let us just see what happens when phi equal to 0, right? If phi equal to 0, what happens to I channel output? That is half AC cos phi into m of t. What is cos 0? Cos 0 is, what is cos 0? That at least you can type in, right? Right. I don't know whether you people are in a sort of protest or, yeah, at least I can see some. Thank you for responding, right? So what happens is when phi equal to 0, this I channel will be equal to half AC times m of t, and the Q channel output will be, what will be Q channel output? Can anyone tell me what will be Q channel output now? Please type it in. When phi equal to 0, what happens to sine phi? Right. So what will be Q channel output now? All of you can see this, right? You can see this. Is it too small for you to what, uh, see? Right. So what happens to Q channel output? What happens to this? What happens to this? Yeah. So people are typing it in 0, right? So Q channel output will be 0, right? So if phi phase error, so when I say phi, it is actually what the phase difference between this carrier used at the transmitter end and the locally generated carrier, right? So when that is equal to 0, right, we'll get in I channel output, right, or in phase. It is actually what it is, in phase. I means in phase, and Q means quadrature phase, right? Q means quadrature phase, right? So Q output will be 0. So when you give a 0 and any other number to a product module, right, the output has to be 0. So there is no error signal here. So which means there is no need of any adjustment, right? So this about this voltage controlled oscillator and PLL in detail we'll study in second module. So that's why I'm not discussing anything now. So voltage controlled oscillator, for time being, we just like appreciate this much. Depending upon the input voltage, right, the output of this VCU will change, right? So only that much you know as of now, right? So this this quadrature phase output will be 0 when phi equal to 0. So then, which means it's in perfect synchronization. Phase is in perfect synchronization. No action is needed, right? But what happens if phi is greater than 0, right? So phi is almost approximately one very small value, right? Very small value. So if you just imagine, so there is a very small phase error, right? When phi is slightly greater than 0 and phi is almost equal to 0, very small phase error. So at that time, what will happen? So here in phase, it will be half AC times m of t into cos phi, right? M of t times cos phi. So when phi is approaching 0, cos phi will be almost actually what will be equal to 1, right? When phi is approaching 0, cos phi will be almost equal to 1, right? So this whatever, if the phase error is very small, whatever I channel output we had, it will almost remain unchanged, right? Why? Because this cos phi will be almost equal to 1, right? It will almost remain unchanged. But if you see the Q channel output, it is equal to what? Half AC times m of t into sine phi. And when phi tends to 0, right, when phi is very small, right, you might have used it in some other places as well. Sine phi actually what tends to phi. For small values of phi, sine phi is almost approximately equal to phi. Have you heard it anywhere? Please say yes or no. Right. For small values of theta, sine theta is almost equal to theta. So you have heard it, right? So okay, you have heard it. It's not the first time you are hearing it. So what happens is the whenever there is a small phase difference, this Q channel output will be proportional to the sine phi, and which in turn will be proportional to phi, right? So that information actually what? So it is given to phase discriminator, and phase discriminator will give an output or error signal, which is actually what proportional to this phi, right? And one more thing, uh, what happens uh, if phi is positive, right? If phi is positive, right, it will be sine of a positive value, right? So one more thing which you have to keep in mind is if phi is positive, sine phi is positive, right? Sine phi is positive, and if phi is negative, sine phi is negative. Why? Because sine phi is an say odd function, right? Sine graph is like this, right? Or else you might have studied sine of minus theta is equal to minus sine theta, right? So it can tell in which direction phase is changing, that as phase error is occurring, right? If phase error is like positive or phase error is negative, so this Q channel can give, right, whether the direction of phase error as well, right? So depending upon that, right, this phase discriminator will produce some error signal, and accordingly what the voltage controlled oscillator will correct the correct its output. It will such that the phase difference is reduced. So it continues, right? It continues like this. So this is a practical method using which we can bring in phase synchronism, right? So it's a practical method using which we can bring in phase synchronism, right? So and one more practical approach is, have you heard of pilot signals? Have you heard of pilot signals? So as DSBSC, it doesn't have like carrier information as such, right? So practically what in some cases actually we'll send some pilot signal which has the carrier information, right? So that is also another method. So in syllabus we have to study only about this Costas receiver, right? So now do you have an idea how Costas receiver works, right? Is it clear? Right, maybe I didn't explain anything in detail about voltage controlled oscillator. Why? Because voltage controlled oscillator as such is a part of our second module. Right, voltage controlled oscillator is a part of our second module. There we'll study that in detail, what VCO and the PLL, all those aspects. Right. So now, are you able to appreciate whatever discussions we have done? So, okay, maybe a Costas receiver, it can detect a DSP-SC signal, and it can actually bring in phase synchronism. How many of you agree that with whatever explanation I have given, are you ready to accept it? Yes or no. I didn't ask if you have any doubt. Right. Mhm. Is it okay? Is it somewhat clear? Not. I'm not asking it about. Is it 100% clear? Right. Somewhat. Did you get an idea? Will you be able to what? If you just sit and think through, will you be able to learn it on your own? Right. So my idea is to tell you how to learn. Not like I'm not here to what teach you people. Right. So I'm just trying to help you out how to learn. Right. I think that's what I'm supposed to do. So okay, actually now I'm getting some response. Thanks. Yeah. So clear. Okay. Thank you. Right. You find others if it is not clear. Right. It's not a big deal. It's not a right very complicated thing. And you can just sit right. Try out writing all these things. Maybe you can right just sit and analyze. Then definitely you will be able to work. Uh, Appreciate this concept, right? So that's actually a Costas receiver, right? So you can see how complicated it is, right? How complicated. What for saving a power which was transmitted in carrier, we suppress the carrier, but the cost in terms of complexity of the receiver and complexity of the transmitter which we have to pay, right? Like that is clear here, right? Whether it is complicated or not compared to our basic envelope detector. Right, even right, we didn't even see actually what a discrete component implementation of this. It's just a block diagram treatment, right? So if you have to implement a product module, so you should have some nonlinear device, right? Then a low pass filter. Again, for that you need some circuitry, right? And VCO. Yeah, so for that also you need others. So it's just a block diagram. What we have seen, that block diagram itself is actually what complicated. So that is the price which you have to pay for saving power, right? So okay, but that is a Costas receiver. Now we'll move on to quadrature carrier multiplexing. So before that, I'll just pause for 1 minute, and I would like to ask if you have any doubt, right? So if anyone is having any doubt, right, may please ask. Right. So now after this quadrature carrier multiplexing, we have only two more topics. Maybe that we'll finish tomorrow. So tomorrow officially we'll conclude module one. Right. So that after quadrature carrier multiplexing, we have single sideband modulation and vestigial sideband modulation. Those things we have already discussed many times in two different sessions. Right. While we were doing a comparison between different types of amplitude modulation schemes, we have already discussed that. So I think we'll be able to what discuss it and finish through easily. So now, if you have any doubt in our Costas receiver, you may please ask. Any doubt? Is there anyone with no doubt? Okay, so no doubt. Right. So now we'll see what is a quadrature carrier multiplexing. So this quadrature carrier multiplexing, right? It makes use of actually what is quadrature null effect, right? So what was quadrature null effect? We just recollect, right? When this phase error is equal to pi by 2 or odd multiples of pi by 2, right? The demodulator output will be equal to 0, right? Whenever the phase error is pi by 2 or odd multiples of pi by 2, the demodulator output will be equal to 0. That is quadrature null effect. In fact, it was an issue with a DSBSC receiver, but same thing can be used to what multiplex two different signals, two different baseband signals, M1 of t and M2 of t, right, which has same or right. So with a maximum bandwidth of W, right, and we can transmit it through a channel with the bandwidth equal to what 2W, right. So that is quadrature carrier multiplexing, and at times it is also called as QAM, quadrature amplitude modulation. But I would never suggest you to what call this QAM. QAM itself is actually another digital bandpass modulation technique which we'll study later in higher semesters. Right? So I recommend you to what they call it quadrature carrier multiplexing. It's a multiplexing scheme. So basically, multiplexing is transmitting two or more signals over the same channel, right? So we have different means of multiplexing. We can either multiplex like by means of frequency division, or by means of time division, or even by means of say at times we can even use some pseudo random codes, and we can spread different signals using different codes and transmit. So code division multiplexing is possible, right? So all those things are possible. So here this is actually what quadrature carrier multiplexing. So it's quite straightforward. It follows from actually what whatever we have learned. This is the product modulator or the coherent detector, right? And the idea of quadrature null effect. So we can see here we have two messages, message M1 of t and M2 of t, right? So those two messages are given to product modulator 1 and product modulator 2, and you can see we do have a local oscillator which produces AC cos 2 pi FCT, and AC cos 2 pi FCT as such is given to product modulator 1, right? And AC cos 2 pi of FCT phase shifted by minus 90 degree is given to what product modulator 2, right? So the output of product modulator 1 will be AC cos 2 pi FCT times M1 of t, right? So I can write it here. So it will be AC cos 2 pi FCT times M1 of t, and here it will be AC sine 2 pi FCT times M2 of t, right? So then we can combine these two and transmit, right? So we can combine these two and transmit as say these two are in phase quadrature, right? Even if we mix them in actually what time domain, right? At the receiver end we can separate them, right? Completely we can separate them, right? So this is a quadrature carrier multiplexing circuit, right? So it's very simple. We have two product modulators, right? And the local oscillator produces the carrier frequency, and that as such or in phase carrier is given to one of the product modulators, and a quadrature phase carrier is given to what other product modulators, right? Other product modulator, and so one signal M of t will be modulating a carrier cos 2 pi FCT, and M2 of t will be modulating a carrier sin 2 pi FCT, and both of them are multiplexed and transmitted, right? And at the receiving end, right? At the receiving end, so what is getting transmitted? I'll write. So maybe S of t is equal to, it is AC cos 2 pi FCT, AC cos 2 pi FCT into M1 of t plus AC sin 2 pi FCT into M2 of t. So we have two messages, M1 and M2, right? So now at the receiver end, so this is the right quadrature carrier demultiplexing circuit. So at the receiver end, we have to what? Separate. We should get back M1 of t and M2 of t, right? So how to do that? So this thing, right? These things in detail, right? You will study in your sixth semester digital communication. There is something called canonical representation of a signal, right? So there you will study further in detail. But now if you are able to understand, if you are able to appreciate the working of a product modulator and a coherent detector, then you should be able to appreciate this as well, right? So so we are giving this S of t here, right? It is a common signal which is given to. So in receiver, what we have is we have two coherent detectors, right? A product modulator followed by a low pass filter, and again it is supplied with some carrier frequency, right? And again we have a lower arm of coherent detector. It is supplied with a carrier signal which is in phase quadrature with the first local oscillator signal, right? So now what we are doing is, so the output of the first arm will be what? First product modulator will be AC cos 2 pi FCT M1 of t into cos 2 pi. So we'll consider only the first term, right? We'll consider only the first term, right? So the output of sorry, okay, first term in the sense we'll consider only this first product modulator. So what we'll have is output of first product modulator would be S of t into 2 cos 2 pi fc t. 1 second. Right, and right. So the output of this first product modulator, it would be S of t into 2 cos 2 pi fc t. So now can anyone actually what help me out with this? So I'll call out a name. If I may call Shreyas, can you please help me out in expanding this?
Yes, sir.
Yeah, please Shreyas, help me out, please. So S of t. So S of t is so first term will be what AC cos 2 pi fct times m1 of t into cos 2 cos 2 pi fct. So I can write 2 AC. It's cos 2 pi fct into cos 2 pi fct. Can I write cos square 2 pi fct? Shreyas,
Yes, sir.
cos square 2 pi fct, right, times m1 of t, right, plus I have 2 AC cos 2 pi fct sin 2 pi fct times m2 of t. Whatever I have written is correct here. S of t into like the signal here is what I meant to ask. S of t into 2 cos 2 pi fct. So S of t is AC cos 2 pi fct m1 of t. So if you multiply it with cos 2 pi fct, we'll be getting this 2 AC cos square 2 pi fct times m1 of t plus 2 AC cos 2 pi fct into sin 2 pi fct times m2 of t. Right. So now now I need someone to help me out with some trigonometric identity. So it is 2 AC times m1 of t. So what is cos square 2 pi fct? Is it 1 plus cos 4 pi fct whole divided by 2? Uh, is it cos square theta is, what is cos square theta? It is 1 plus, is it correct what I have written? Or please do correct me if I am wrong. Someone?
Correct.
Correct, right? So, okay, I can write it here. Right. 1 plus cos 4 pi fct, right? 1 plus cos 4 pi fct divided by 2. So that divided by 2 I am writing here. Right. I am writing it here. So, and second term would be, this is 2 AC. What is cos theta sin theta? Cos theta sin theta, or 2 sin theta cos theta, that is sin 2 theta, right? Yes or no? Right. 2 sin theta cos theta sin 2 theta, right? Maybe that is the only what trigonometric identity I can recollect anytime. If you ask, I don't know how. Somehow it got registered, right? So so 2 sin theta cos theta, it is sin 2 theta. So we have here actually what 2 sin theta cos theta, or cos theta sin theta. That will be actually what half sin 2 theta, right? Or AC into m2 of t into half I, okay, half I'll right, half I'll write here. It is sine 4 pi fct. So till here what I've written, is it correct? Right. Whether it makes sense, I'm writing the output of first product modulator. Right. You know this multiplex signal is actually what? AC cos 2 pi fct times m1 of t plus AC sin 2 pi fct times m2 of t, right? And we are giving it to a product modulator, and on the upper arm it is getting multiplied with 2 cos 2 pi fct. So after getting multiplied with 2 cos 2 pi fct. I have written it like this. Is it correct? Can anyone like give me an assurance? Yes, right. So now what happens is this is fed to a low pass filter, right? This is fed to a low pass filter. So maybe I can write it as actually what? AC times m of t plus AC times, so m1 of t, right? AC times m1 of t times cos 4 pi fct plus AC times m2 of t times sine 4 pi fct, right? So now this entire thing is passed through a low pass filter. Now we'll just identify which are all actually what uh, a low pass filter which will allow the maximum frequency content of m1 or m1 of t, m1 of t or m2 of t. So this one is a low pass signal, right? It doesn't have any cos 2 pi fc or 4 pi fc term. So this is a low pass signal or low frequency signal. But if you see here, this is a high frequency signal, right? And this one is also a high frequency signal, right? Are you ready to accept that what I told? Right, please, someone, if you can, please respond. Right, I can at least make sure. Yeah, you have heard. So, do you have another session at 3 today? CRs, anyone of you can, if you can respond. Do you have another session at 3? I'll wind it up soon. Maybe I'll take some 2-3 more minutes. Right, do you have another session now at 3?
Uh, I think it's there, man. Wait a minute. Not
Right.
the course, I guess. Lisa ma'am have told something. So it's at 3 p.m. It's at 6. Yeah, no, sir, no, sir.
Right. So as per timetable only, this is there. If okay, yeah. So maybe we'll finish off this fast. So you can just you just write it down and try to find out. So right. So we have a low frequency signal, right? Then these are high frequency signals. So when it is passed through a LPF, what happens is these high frequency parts will be eliminated. So what we have is only low frequency part. So in the upper arm, we are getting AC M1 of t, and similarly, if you write it for the lower arm, right, you will get AC times M2 of t. So you can, without any actually what contamination, right? Of course, there is a scaling of amplitude, right? Amplitudes, there is a scaling of amplitude. Apart from that, right, without any distortion in amplitude.
So
right.
sorry to interrupt. We
Yeah.
have class at 3 o'clock. Some introduction of networking.
Is it?
Sir, it's not a class. It's like a session. I think
Yeah,
HOD is
session.
hosting it.
Is it? Okay, fine. So I'll just wind up now, right? So we are getting the demultiplex signal at the output. So here again, the phase synchronization is a problem. So to assure phase synchronization, what you should do is the receivers you should be actually what Costas receiver. If you use a Costas receiver instead of actually what normal coherent detector, you can get over the problem with phase synchronization, right? And otherwise, what you should do is you should transmit a pilot signal so that phase synchronization is assured. So with that, maybe we'll wind up the session, right? So we have learned about Costas receiver and quadrature carrier multiplexing. So we have a session tomorrow morning. So tomorrow morning session we'll discuss about SSB and BSB, right? So that's it. Maybe we'll end this session here, right? So thank you for joining. All of you can leave, right? If someone is having any doubt, but I think as you have a session, right, so you will have to leave now, right? Not a problem. Thank you for joining, right?
Thank you, sir.